second tutorial of this course, Reinforcement Learning. I am Avik Kaur, a PMRF fellow at Indian Institute of Science. So in today's tutorial, we'll go through these topics. We'll recap once the bandit and RL setup that we have introduced in last tutorial. As told in the last lecture, or last tutorial, we will cover planning algorithm for finite horizon MDPs. Then this week, there are several bandit algorithms, multi-arm bandit algorithms are covered. So we'll see some of them, and then we'll see how to code those algorithms and observe the regret performance. So from now onwards, we'll say maps to say multi-arm bandits and MDPs, which is typically the model for RL setup. So in case of maps, we have an action space and a reward function, mu. And in case of MDPs, we have a state space, we have an action space, we have a reward function, we have a transition probability kernel, and we have a episode duration. This is called finite horizon MDP. So in map setup, we play action each time. So this is the time horizon starting from t equals to 1. So we take some action A1 and receive some reward R1. Take some action A2 and receive some action R2. Sorry, R2. Now here, the thing is R1 is sampled from some distribution that is denoted by capital D. And this distribution is specific to the arm A1. And expectation of R1 given A1 equals to A is basically this mu of A. So mu of A is the expected reward for playing action A, or in other words, in bandit literature, playing action is also called pulling an arm. Okay, so this is the map setup that you are introduced to. And in MDP setup, again, we have horizon equals to 1. There is some state S1. And upon observing that, the agent takes an action A1 and receives some reward R1. and then the state changes to S2. Again, action taken A2 and received some reward R2. State is changed to S3. And here, how this reward function is reward function affects the immediate reward. So R1 is basically some sampled from some distribution. Distribution changes with state and action. And here, expected value of R1 given A1 equals to A, when S1 equals to S and A1 equals to A is mu of S comma A. And this transition probability kernel affects the next state given the state and action at the current point. So probability that S2 equals to S prime given S1 equals to S and A1 equals to A is E S A S prime. That's how the transitions are governed. So today we have said that we'll. So then we have also discussed that what is the difference between what is RL and what is planning. RL is when you want to control uh, the system.
Sir, what is S prime?
Yes.
What is S prime? S2 is equal to S prime.
So can you please clarify the question again?
No,
We heard something.
probability S2 is equal to S prime. You are telling what is the S prime in that?
S prime is some state. So you have a state space, right? For your problem, there is a state space, which is this calligraphic S. Now S prime is any state from that uh, state space, and so is S. So this is telling you that S2 is the random variable that takes the value of your system state at time 2. So at time 2, you will be at state S prime given at time 1, your state was S and you have taken action at time 1, A, given that two things, S1 and A1, what is the probability that in the next time step, that is time 2, you will be landing in state S prime. And that probability will be given by this transition probability kernel evaluated at the triplet S, A, and S prime. Is it clear?
Yes, sir. Yes, sir.
Oh. So, yeah, then we have also talked about what is the difference between RL and planning or control. So in planning, we say that we know the two things, planning and RL. So here we know the system. Here we don't know. So that is the basic difference. So for finite horizon MDPs, we'll go through basic planning algorithm called value iteration or dynamic programming. Has any of you come across this dynamic programming, this term? So to prove the results of this dynamic programming algorithm, we'll have some assumptions. One is this state space and action space are finite. And second is this reward function is bounded function. So I hope you know this. What do you mean by bounded function? That is, mu is mu of SA is less than some constant p for all SA. State action space for some p in fields.
By finite, do you mean discrete?
Yeah, finite has to be discrete. So discrete is a superset. I mean, all finite sets are discrete, but all discrete sets are not finite.
Makes sense. Thanks.
For example, number of all natural numbers is discrete, but not finite.
Understood. Thanks.
Yeah, someone said something. Was it a question? Okay, I'm assuming there is no question. So we'll define something called policy. So policy is a map, collection of maps. So policy is a collection of maps, or you can call function from phi h. H is representing the time step here. From state space to delta A. I'm explaining what is delta A. H equals to 1, 2. We start from 0, 0, 1, 2 to H minus 1. Capital H is the horizon length, or also called episode length. So applying pi, okay, sorry, some explanation is due. So what is delta A? This is called simplex over set A. It is just a name, but what is that? This is basically the space of all probability distribution on A. Say A is 0, 1. This line, say, this is 0, this is 1. So 0.4 and 0.6 is a valid probability distribution on this set A, right? So this 0.4, 0.6 belongs to delta A. Okay, so that's what it means. The set of all probability distribution on some set, that is simplex over that set. So applying policy pi on MDP S A mu B H. So we'll denote MDP by this 5 tuples, means sample action AH. AH means the action you are applying at step H from the distribution. So phi H of the state is T. This is a function from state space to the simplex, to the space of all distribution over action set A. So phi HST is basically a distribution, right? So this policy is giving you a given the states state at time t, the policy is giving you a distribution of actions, and you apply policy pi, means you sample the action AH. Sorry, I have mixed up H and T. Sorry, SH. You sample action AH from the distribution phi H SH. Is it clear? Tell me if it is not clear. So that's what it means as applying policy pi. Now, this is called a randomized policy. Also, I'm not sure whether you are already exposed to Markov chains and all, but this is also called Markovian policy because the decision at time h only depends on the state at time h. So that is the reason why it is called Markovian policy. Because on a MDP, if you apply a Markovian policy, the entire state process becomes a Markov chain. Randomized policy also Markovian. So this is because takes action in a randomized way. And this Markovian, that is because I think this policy, what I do, randomized Markovian policy. Markovian because takes action depending on only current state. So it is observed that, and not observed, sorry, wrong word. It is proved that for any Markov decision process, Markovian policy uh, can optimize the process. I mean, the optimal policy, uh, there exists at least one Markovian policy that optimizes, that is the optimal policy for the Markov decision process. So when the system is modeled as MDP, then we need not to look beyond Markovian policy. We do not need to take action that depends on previous states or previous actions as well. So in this course, everything will be confined in Markovian policy. But randomized is probably a bit unnecessary all the time. So we can define something called uh, deterministic policy. So let us write that. Let me add Markovian as well, because what I'm going to define is Markovian. So phi is collection of maps, phi, which are functions from state space to action space. Requesting to join, but I cannot see the request. So here applying this policy pi means playing PH SH at time H, right? So VHSH is basically an action, one single action here, because the uh, map VH maps to maps from state space to action space. So this is deterministic. There is no randomized component here. So you are not sampling from any distribution. Okay, so this policy is one of the important thing in this course. So uh, after introducing to policies, let us now discuss what is value function of a policy. Let pi be a policy, deterministic or randomized, but necessarily say Markovian, because we need not to think beyond Markovian. X naught is defined as expectation of mu. Okay, so Okay, so I think I have to go back to the definition of MDP, and for the sake of generalizing to the most general uh, thing, I think I need to change some definitions now, which is basically this mu. Instead of mu, we can replace this as mu h, function from state and action space to say some interval. 0, 1 is the most common and helps us to analyze bit easier. For h equals to 0, 1 to h minus 1. And similarly, we can replace uh, transition kernel by a collection of transition kernel, ph, and I think I hope you remember all those conditions of transition kernel, because it has to be uh, a probability distribution at whenever evaluated. Uh, so if you consider the vector uh, that E is A dot so on, but your third variable is changing over all the state space. So this is a probability distribution. So that condition you have to put, and that will be satisfied for every h, where h will be running from 0, 1 to h minus 1. So earlier, what I was saying is there the reward function and the transition probability kernel was constant over time. I mean, at time 1, whatever reward function was there, and transition law was there, transition kernel that was governing the transition. It is not necessary that at time 2, the same reward function and same transition kernel will be governing the transition. So there is a non-homogeneity here. So this is much general setup. That's why we are shifting there. So if you can have much general, you can have algorithm or results for a general setup. Why don't you do that? So yeah, that was the reason. Instead of x, I think let us write s. So value function is a p pi is a function from state space to reals. And to be more specific, it will be actually okay. That's fine. We'll see. Okay, so what I have written, uh, value function at S is, so if you just expand this, what it is, mu 0 is 0 A0 plus mu 1 S1 A1 plus so on. Last term is mu H minus 1 SH minus 1 AH minus 1 plus mu H SH, and given all the conditions that I have put. What are the conditions? That is, your start state is S, um, where the function value function is evaluated, this Vs, and you have taken action according to the policy pi. Now here I have considered randomized policy because that is the general one, and the policy is Markovian. So here I want to ask one question. I have missed this expectation. Uh, so this is an expectation, right? So we take expectation on random variables. So can you spot the random variables in this expression? Anyone? What are the random variables here?
SH and AH.
Yeah, come again.
SH and AH.
Yeah, right. Thank you. Okay, and there is another caveat. In the last step, at capital Hth step, there is only SH, and there we are not taking any action. So the reward function is that is, you can consider that is some terminal reward. So one example where you can model this thing, I think I have some example. Let me see. Okay, so for a moment, yeah, let us see this example.
Sir, can I ask a question?
Yeah, sure.
So typically value function, do we take at a state level or do we take for the entire episode? So because the heading says value function of a policy, but while you write it as value function of a state and then you are summing up. So how to
Oh,
read this, sir?
yeah, so value function of a policy means you have kept your policy fixed. Okay,
Okay.
and the value function, the domain of the value function, irrespective of the policy, is uh, the state space, and its range is real numbers.
Okay,
So
got it. So
two
the
things.
policy is
One is
fixed by following
policy.
that policy. How are you? Yeah, okay, got it, got it.
Policy you can think as a parameter. Okay,
Hmm,
so
hmm. Understood, sir. And the notation, sir, if I can ask, the notation that you follow here, some literature use T as a time, for example, but I think you are using H as the step value or something, right?
yes, so typically in RL literature for finite horizon setup, that is what we are discussing. There H is used. H and yeah, mostly H is used. I think you are talking
Okay,
about also infinite horizon MDPs. There
yeah,
T is
correct.
used. I agree. Yeah.
Understood. Okay, thanks.
So this example is from like inventory control. Uh, And this kind of examples were actually the motivation to start this area back in, I think, 50s or 70s during that. If you read the first chapter in I think Martinell Puterman, you'll see there are some real life problems which are solved by this value iteration things. So just a second.
Sir, which book you told? Can you write on that name?
Yeah, name of the book is Markov Decision Processes. Writer is Martin L. Puterman. But that is, I think that will be a overkill to read that now. So for a short introduction, I think you can go through Sutton and Bartle. That also has fairly elaborated discussion on Markov decision processes. Yeah, but if you want to like do research and all, Martinell Puterman is one of the best. Okay, so let us see the this example. There are lots of things which are written, but I will not write all of the things. I'll say some things. So one particular type of item is there to be stored in a store. So one item, and the store has capacity capital C, which is a natural number, say 100. So the store can at a time can store at most C unit of items. So ST is state, which is number of items at time t. Okay, so I'm using H. Better to use H. Time H. And action AT is so AH is number of items ordered at time H. So AH has to be from this set, right? You can order 0, that is nothing, 1, so on, up to C minus SH, right? Because if you order more than C minus minus SH, then you cannot keep that. And the evolution of the system follows this rule. SH plus AH plus WH. Sorry, minus WH But what happens if this quantity is negative? Then it will be max of this and 0. So what is WH? That is the main question at this point. This is demand. And it is an random variable. A random variable. So what happens at time t? At time t, you have ST items. Say this is t minus 1, t plus 1. And then you see you have ST number of items, and then you order, you are the, say, storekeeper. You order a H number. So again, SH, H number of items you are ordered. H. The assumption is if you order it, the items will come instantly. So as soon as you ordered, the items, AH items have come. And during this time period, say for practical problems, say this is 1 week. During this time period, WH number of demands have come. And so if WH is less than SH plus AH, you can serve demand to everyone. If it is more, then there will be some unfulfilled demand, right? And I think now this update equation of the state makes sense, right? You cannot sell things which you don't have, so there is this truncation at 0. Now this probability, transition probability. So WT is a or WH is a random variable. So based on the distribution of that random variable, you can have a transition probability matrix. So if you want to solve this problem using value iteration we have not discussed yet, but if you want to solve this problem, you have to model it correctly. So you have to estimate this demand distribution correctly. That's all you need, given you know the algorithm. And also, you need to find a reward function, right? Reward function for this economical things, reward function is very simple. It's the profit or the loss, right? So how do you model that reward function as well? Mu, for the timing, let's keep this reward function homogeneous. That is same for all the time. Mu of S H A H W H is say the unit selling price is S. So it will be maybe S is for selling I'm in S, but S is also state. Let's write it. J times min WT XT CT. So if you have more than demand more than XT plus UT, then you have not sold it, right? You have at most sold XT plus UT. So you take mean with that number. And for each item you have sold, you have gained this J price. And say unit purchasing price is B. So B times UT, you have X, that is your expenditure. for buying the item. So B times UT you have lost, and say you have not sold some, you could not sell some items in a week. So there will be a, for example, this scenario demands some cost incurred for not selling, not being able to sell, or there might be some cost related to uh, not able to fulfilling some demands. So that you could have achieved some gain, some profit there, but because of bad decision, you could not. So selling more or selling less, both are due to a bad decision. So say there is a loss associated with it, and that is minus, say that loss uh, per item is L ST plus, oh, I have again shifted the notation, sorry, ST and AT. Again, this is AT. ST plus AT minus WT. Okay, so at the last stage, mu H will be having only SH. There will be no demand. So let's say that is L times SH. So that you will not be able to sell. So that items will be left with you, and that is your loss. So that is a perfectly reasonable reward function. And then you can, by estimating this demand random variable, you can construct your transition probability matrix. So I'm not very good at changing the notation on the fly.
One question is the loss, there is a loss even if SS plus H is higher than WH, is it?
S plus H is higher than WH. Yes. So I mean, I have not modeled it, but they're saying that it is the storage cost. So that is,
Okay,
say
okay. And
the item is something like cheese or butter. So
yeah, the loss is similar whether it's a storage cost or whether WH is higher than SH plus H.
yeah, if you cannot fulfill the demand, yeah, that can be different cost.
Okay, okay, got it.
It's just
Got it.
modeling. You can
Okay,
you can do it mathematically, right?
okay, cool.
Not a big. Okay, so let me explain this. If S prime is if the next state is higher than uh, current state plus current action, that means currently you have S plus A items, and the next state is higher than that. That is not possible by the nature of the problem. So uh, no one will give you items in the from H to H plus 1. So that probability is 0. Now, if S prime is greater than 0 and less than equals to S plus A, that is a perfectly feasible condition. And there, if your demand is S plus A minus S prime, then only that will happen. And if S prime is uh, 0, that means next state is 0. That means demand was at least S plus A uh, or more than that. So those probabilities you can add up till infinity, and that's your transition probability matrix. I mean, transition probabilities, and you can form your transition probability matrix. Okay, so that's the model. So this is an example of finite horizon Markov decision process. And let us now move to value iteration. Yeah, so we have introduced what is V pi S. It's expectation. So this next condition I was going to write is actions are taken as per policy pi, right? That was the condition. So that I can I denote it in the expectation itself. So instead of writing that condition, I modify my expectation operator. And we define something called optimal value function, which is not a function, not a parameter, not parameterized by any policy. V star denoted as V star, function from state space to reals, like the previous. And this is defined as V star S equals to sup, or can write max because there are only finite policies. Max over, okay, so there is not finite policies, sorry. Randomized, since we are also considering randomized policies, there are infinitely many policies. So over pi. So this capital pi is all the policies, all the randomized Markovian policies. Or actually, for the moment, we do not know that a Markovian policy will maximize this uh, thing. So let's say pi, capital pi is set of all policies. So we say pi star is optimal if V star S equals to, so pi star is a policy, right? V pi star S for all state. Okay. So that is the definition of optimal policy. Now we come to the main theorem proposition. For every initial state is the optimal value P star X is of the MDP. So when I'm writing mu and P, you think it as the collection of reward function and probability transition probability kernels, which changes from time to time. Is equal to V0 case. I have not defined what is V0. So where V0 is given by the last step of the following algorithm. What is the algorithm? That is VH SH equals to RH, sorry, mu H SH. And for H less than capital H, VH SH is max over A in action space. So here I have, I think I should write it differently. So this is, I'm denoting SH as random variable. So here it is not random variable. This is defined on every state. And mu H is function of also the action. It's prime in the state space. S A S prime V H plus 1 S prime. For H equals to H minus 1, H minus 2, so on, 1, 0. So what you do, so this is planning algorithm, right? You know the reward function, you know the transition kernels. So knowing that, you start from step H. You define V capital H, which is exactly the terminal reward function, mu capital H. And then you go at H equals to H minus 1. In this step, what you don't know, given you have VH. VH you already know because you know the reward function. So in this step, you know mu H, that is mu H minus 1. You know the transition kernel. You know VH plus 1, that is VH. Right? So you can compute this function VH minus 1. So let me write it for you. Max A given A, mu capital H minus 1 S comma A plus summation S prime over state space P S A S prime V capital H S prime, and V capital H is R mu H, mu H is prime. Right. So you know everything. Now at this step, you also know VH minus 1. So you can compute VH minus 2 at every state, and so on. So you keep on computing this, and you will, at some time, you will arrive at V0, and you can compute at every state S. So that's what this dynamic programming algorithm is. Okay, so this is the algorithm, and have everyone understood? Can I erase this part where I have explained? If not, someone, I mean, if you need some explanation, then stop me now. Okay, so I'm erasing this part. Okay, so what is it is telling? This following this algorithm, you will get some function V0, and V0 is exactly your optimal value function. That is excellent, right? Uh, that's what you wanted, but that's what not all you wanted. You also want optimal strategy or optimal policy, so that you can take those decisions in your real life problem. And if you are the storekeeper, then you can maximize your profit. So that part now. Furthermore, if uh, AH star equals to PH star, PH star is some policy, SH, where PH star is a deterministic policy because we are writing equal to, we are not sampling. It's a deterministic policy. Uh, Not policy. Policy is the collection of such maps. A deterministic map from state space to action space. That maximizes the RHS of, say, this equation is star of star. That means that maximizes this, the maximizer of this operation. Then, okay, for each case, I think I should, yeah, this should be S, not SH. For each S in the state space, and for each step, each age, then this collection V star to h minus 1. So at h, there is no action to be taken. So there is no, the policy doesn't make sense. Okay. So this policy, let us denote it by pi star, is one of the optimal policy. So there could be another optimal policy which may not be Markovian, may not be deterministic also, but this one will be one of the optimal policy for the problem. Okay, so now time is a bit less. So I think in 15 minutes I can prove this. So we prove it by induction, and to be specific, backward induction, because the algorithm starts at capital H and goes backward. So let's say pi is a policy. Just collection of this policy pH. Then we denote pi h as the policy. I think I should write this index where h is running from 0 to h minus 1. Then pi h denotes the collection that of pH, where h starts from h, or h prime starts from h. H is the running variable, so let me write it h prime. Pi h prime is where h is running starting from h prime plus 1, so on, h minus 1. So pi h prime is subset of the collection pi. Well, what will show? Will show that okay, let me define something. So we have defined something, just V star. So now we are defining V star H of S. That is basically max over all pi H. Pi H means starting from H to H minus, capital H minus 1. All policies of that type. Max over all such policies. Expectation over pi H, where you take action according to policy pi H. Mu capital H SH plus you start from step H So H prime equals to H2, H minus capital H minus 1, mu H, so H prime, S H prime, A H prime, and SH is says. Yeah, I think H prime is the running variable. That's better. Yeah, so I think now things are confusion free, but if you have confusion, please ask. Okay, so what we want to show. We'll show that VH star is equals to VH. VH we are obtaining from the algorithm, and VH star is this truncated value function, optimal value function, you can say. So because you are starting from step H and going till step capital H. So I think now why we will prove this thing using induction method, that is much clearer, because we'll show for capital H, then we'll assume this equality at some step H or H plus 1, and then we'll come to step H and show the same relation holds at step H as well. Okay, we'll show this, and which will mean basically V star. V star is equals to V0 star. And by induction, we'll show that this is equals to V0. So this is the last step, and that is our goal. So the base case is H, small h equals to capital H. VH star S is equals to, because there is nothing to maximize, there is no decision to be taken. That is equals to VHS, and that is equals to mu HS. So they are equal, right? So there is no confusion about base case. Now induction hypothesis. So what is induction hypothesis? That is V star H plus 1 equals to V H plus 1. Yeah, that is our induction hypothesis. And okay, so there will be some notational things that will be coming in the next few steps. So V star VH star S equals to, by definition, max over all this truncated policy pi h expectation, even plain policy by h, mu capital H S H plus H prime equals to H minus 1 mu H prime S H prime A H prime, that is by definition, and SH equals to S. So if you see pi H, this is a collection of policies in a sequential way, right? pH plus 1, pH plus 2, and so on till pH minus 1, capital H minus 1. So we can write this as pH and pi H plus 1. So the rest of the term after pH, that is basically pi H plus 1. Why? That we'll understand in a moment. So continuing from this line, so start. So we can write this as max over pH expectation. We're not writing on what. So let us write this first reward mu H SH AH plus the rest. So when you are taking action AH, you are not looking at any the policy pi H plus 1 because that will come next. So this maximum you can take inside max over pi H plus 1 expectation over pi H plus 1 subscript. And then you can write mu H SH plus H prime equals to H plus 1 to H minus 1 mu H prime is H prime AH prime given SH equals to given SH equals to S, right? So this inner thing is mu H SH plus H. This inner thing is basically by definition is VH plus 1 star SH. Sorry, my bad. SH plus 1. So this is nothing but expectation of mu H SH Okay, let me consider this is a deterministic policy. So this will be So from policy, we are shifting to action because this pH is only influencing AH. And this is exactly max for A. Mu is A. And this expectation will not of, will not affect this S and A because we have already fixed S and A. It will affect SH plus 1. How? So we have to take an expectation over next state. S prime belongs to state space. BS A S prime. PH plus 1 star S prime. Yeah. So that's the thing. And this is exactly VH is, right? That's what we have defined. So we have proved the first part of the claim. And for the second part, we can again do it via induction. Let pi star h plus 1, pi star h plus 1 is optimal for the h minus 1 step problem. So I guess you understood what I mean by h minus small h minus 1 step problem. So it's starting from h plus 1 and ending at h. Well, so VH star S and say pi star H is P star H. P star H we have defined earlier. So here we have defined what is P star H. That is the maximizer of the right hand side of the dynamic programming equation. P star H concatenated with the rest of the policy pi star H minus 1. So I'm not proving it because we are running out of time. You can show that pH star S equals to expectation of pi star H. Sorry, pi star H. Mm, So the capital H minus 1 step problem. So if you show that, then it means pi star H is the optimal policy for the capital H minus 1 step problem, which is exactly the induction hypothesis you had in H plus 1th step. So you have a dynamic programming algorithm now. So what I suggest is construct an MDP of your own in your favorite programming language and try to apply this algorithm. This is a very easy algorithm to code. So yeah, try out. So now we'll discuss about this multi-arm bandit algorithms little bit, and we'll uh, go for coding it. So I have already coded, so I'll just describe the coding. So, yeah, so audience is silent for quite some time. Is there any question or was it unclear? Any feedback? Okay, someone is asking about um, references. So I told Martinel Kuterman. So one of the uh, one of the better reference for like concise and also elaborate introduction on MDPs is optimal control and dynamic programming, or I think the other way, dynamic programming and optimal control by Dimitri P. Bersekas. So this book I can I'll suggest. Let me write the name itself here, the chat box. So I think in chapter 1, there is a very nice way they have introduced uh, finite horizon MDPs. Well, so now we'll go for bandit algorithms. I'm not sure whether you are also introduced with explore then commit algorithm, uh, but we'll discuss that. Its analysis is nice. Explore then commit. Was it discussed in any of the lecture?
No.
Okay. Okay, then I think you will know another algorithm, and its analysis is like the tool sets are very similar to UCB and much simpler algorithm. So the algorithm I'm describing, you need inputs, some parameter. It's called exploration parameter. M, and yeah, you know the system, so you also know the number of arms. Okay. So the idea is you'll be given a time horizon, and until a round, I'm not writing it, giving any notation to it. Until that round, you will play all the arms uh, in round robin fashion, and there your regret performance will be very bad. And after that, you will choose one arm and play it throughout. So what until here, whatever you the information you'll get will see based on the estimate whatever is the base term, you will play that term. So the algorithm is very simple. For t equals to 1 to capital T, IT, that is, let's just write AT first. So M is the exploration parameter that say means you will explore every arm, play every arm in that round robin fashion, first exploration phase. So this is called exploration phase. And then it is called exploit. So in exploration phase, you will play each arm m times. So this time is basically m times k. So p mod k plus 1. If you are denoting the arm as the arm set is say 1 to capital K. So you'll choose arm in this fashion, that is round robin. And whenever you are done exploration phase, you choose action from action set that is maximizing your estimate mu hat mk. We'll write the expression for estimate, but I think in the course it was denoted by q. I think yeah, there will be no confusion in this. So mu hat t a is basically sum over I equals to 1 to t, indicated that you have chosen at time I a times the reward you have incurred ri by total number of times you have picked arm a. So that is your estimate of the reward, mean reward.
Excuse me, sir.
Yes.
Sir, you mentioned that this algorithm would be run in a round robin fashion. Could you please explain once?
Oh,
about it?
yeah. So this line is explaining that. So there are k arms and your parameter is m. So at t equals to 1, we'll choose arm 1, k1 equals to 1. 2, we'll choose arm 2. At k, we'll choose arm k. Okay. And then at k plus 1, you'll go again at arm 1. And you'll repeat. So at 2k, you'll be at a2k will be equals to k. And you'll do it like till this point, you have done it 2 times. So you have to do it till m times. Is it clear?
Yes, sir. Yes, sir.
Oh, yeah, that is called round robin fashion in literature. Okay, so Okay, so before analyzing the regret, so we'll analyze the regret of this algorithm. But before analyzing the regret, we there is something called instantaneous regret. Sorry. So instantaneous regret is basically mu star minus mu uh, minus mu of AT. But I'm not talking about that. So pardon. I'm talking about instant dependent regret. So these two are very different things. Instance dependent regret. So what it means is your regret upper bound. So R of T, say, that will not be that will contain some term of the which is a parameter of the problem. So typically for bandit problems, your parameter of the problems are like sum of suboptimality of each arm. What is suboptimality? Suboptimality of arm is mu star delta A is mu star minus mu A. So this when your problem changes, this term changes, right? This summation. So this is an instant dependent term. So if you have instant dependent regret, that means you are incorporating some problem specific parameter in the regret, and when that problem specific parameter has better value, then your regret will be less, and when that will have worse value, then your regret will be higher. Okay, so that was just a term which I wanted to introduce. Okay, just a second, I have to receive a call. Yeah. So yeah, we have introduced what is called instant dependent regret. Okay, so I think you were already introduced how to how we generally decompose regret. So expectation of regret, that is expected regret, is basically written as sum of regrets due to each arm. So expected number of times arm A is pulled till time capital T. Let's say that is NTA times the suboptimality of arm A. So that's how you decompose regret. Now, for this algorithm, what we want is till time capital T, how many so say for arm A, it has suboptimality delta A. The question is, in expectation, how many times arm A is pulled? So we'll derive one upper bound NT of expected value of NTA. So see, in exploration phase, every arm is played small m times. So that will be included. Small a will be included. Now, with some probability, it will be played. With some probability, it will not be played. So when will it be played? So if mu hat mk, where we are stopping exploration and looking at the estimate, mu hat mka is greater than equals to mu hat mk a star, right? So mu hat a star is the optimal arm that we are considering. Now, let me write this clearly, that arm A will be selected in exploit phase if this happens, right? So expectation of some,
It will be selected when it is greater than every other arm, no? Not just A star.
right, because yeah, you are right, but this is a larger event. So if you bound, the way we, yeah, you're very much right, but the way we are going to bound this, we want to one upper bound, right? So this is enough to generate an upper bound. You'll see in a moment. So expectation of NTA is equals to 0 if it is not selected, times the probability that it will not be selected. Probability that A will be selected. Plus T, capital T minus MK times probability that A will be selected. So the first term you can safely ignore, and A A will be selected. Is basically an event which is basically mu hat mk a greater than mu hat mk a prime. Mm, whatever you have said, I think Nikhil, right?
Yeah, that makes sense.
Yeah. So this is the intersection of the events. And if you just take one event out of that intersection, the probability of intersection will always be less, right? Because the set is smaller. So this is upper bounded by t minus mk. Probability of mu at mk. Okay. Okay. Now this is upper bounded by Hoeffding inequality. This is upper bound. This probability is upper bounded by t minus mk. So all you need to need now is to choose this m carefully so that you can have uh, sublinear Richtet bound, right? So what value of m you can choose? So currently, I need to figure it out. M equals to say okay. If we take this, let's say what happens. Then p minus delta I square by 4, that will be cancelled out. 4 by delta I square. Okay, so delta I is arm specific. Okay, so I think I should have written delta A. Okay. So delta A is the suboptimality of arm A. Now when you are doing this algorithm, you have to look at the worst possibilities. What is the smallest delta A? So let us denote this delta mean as minimum of A not equals to A star, that is not the optimal arm, then it will be 0. So minimum of all suboptimality of the suboptimal arms, not the optimal arm. So when you're choosing M, you cannot choose based on some arm. You have to look at the worst case, delta mean. So delta A by delta mean log square root t. So this is minus something, something big, and I think it will be one less than 1 by square root of t, and then the regret will be expected regret will be less than m plus t minus mk times 1 by square root of t. And this will be, I'm removing the constants, delta mean equal minus 2 log square root of t plus square root of t. We can neglect the negative term. So yeah, that's the regret we have. Yeah, so I'm not very sure that this analysis is the optimal analysis, because this that depends on the value of m. So if you can find some better values, that is also probably possible. Okay, so we are almost at 9, so we'll quickly go through the codes. So I have not coded this explore then commit. But what I'll do is I have coded UCB and Thompson sampling. So those codes will be available to you for read. And what I suggest to you that you also code other algorithms like explode then commit is naive algorithm. So you can code, of course, code that, but there are some other advanced algorithm like KLUCB, that the one I can remember now. So what I suggest is go read those algorithms and try to implement in the same Jupyter notebook file. And if you can do that, then please share with us. Everyone will be benefited from that. Is the screen visible?
Yes.
Okay. So I'll just describe what I have done. I think you all are very familiar with Python coding and you will understand very easily. So first I need to know what is the number of arms and what is the number of rounds we'll play the algorithm. And given the number of arms, I have created a class of stochastic multi-arm bandit, which will randomly generate arms with their mean reward. And here, basically the uh, uh, generation of the reward is Bernoulli. So given mean reward, say mu a is say 0.4, then with 0.4 probability it will generate reward 1, and with 0.6 probability it will generate reward 0. So you can think of something sophisticated, like continuous. I mean, the reward random variable is continuous. That is, the distribution is continuous. So to instantiate, I have instantiated one environment, one stochastic multi-arm bandit, and there is a function for writing the mean of the algorithm. I mean, of different arms. So here are 10 arms, and you can visualize this that arm 1 is the best one. So I think instead of writing arm, I have written expert. I should change that. Okay, so arm 1 is the best, and I think arm 8 is the second best, and the gap is very minimal. So these gaps are so that is delta mean, what I have just written, and the delta mean is very small here. And the regret bound of etc export then commit, if you see the expression that I have derived, that is 1 by delta mean square. That means if delta mean is very small, then the regret will be high. So this is an example of bad instance. If this delta mean was quite large, then the problem would be easier to understand. Okay, so the gap is the minimum gap I have printed, that is 0.011. Fine. Now the algorithm. So this is the round robin part of UCB, because in UCB also you need at least one. Once you have to play one arm, because you are estimating. When you are estimating, you will divide the number of times you have played. Right. So yeah, that you have to do. And here, in one step, I have so inside this argmax, this is basically the UCB index that you have seen in the algorithm. This is the UCB index that is computed, and then you take whichever arm is maximizing that UCB indices. So this is an array. So for all the arms we have computed, and then we have taken the maximizer. That's what exactly the algorithm is. Then we have got the reward, which is returned by the environment. And so environment.get reward is the function to get the reward, sample from that distribution of particular arm. And we have stored the rewards, and you know how to plot regret, best reward minus what you were getting. That's pretty much it. This is very simple, right? And then you can do one test plot, and then you can average over multiple runs, plot the mean and standard deviation in the plot. So those all we can do. And yeah, now Thompson sampling. Thompson sampling is to understand Thompson sampling, you need to read a little bit on prior posterior distribution. For this is also Bernoulli setup. So beta distribution is I think, let me open a new tab, and yeah, maybe you can type this, and you can read one of the link. You'll understand what I'm talking about. So as if your samples are from beta distribution, your posterior probability will be from Bernoulli distribution, your posterior probability will be beta. So those are called, I think, some prior posterior conjugate, if anyone can remember. I don't work in this area, so I forgot. Anyway, so the algorithm is very simple. So first you start with some prior probability, which is this theta, and you theta is basically your estimate estimate of the distribution, and then you can the estimate of the parameters, that is the Bernoulli parameters, and then theta is sampled from that beta distribution, and then you act as theta is your true parameter and sample and play the best term from that parameters. And yeah, that's it. That's the algorithm. And then you, based on what at arm 80 you have done, you have got, if you have got 1, then you update success, and if you got 0, then update failure. And that helps to so the success failure changes your distribution from which you are sampling the theta, the parameter of your bandit. And as you go on sampling more arms and more arms, your theta, the standard deviation of theta goes to 0. So as you sample more, you are more sure about where your true arm means lie. So Thompson sampling algorithms, I mean posterior sampling algorithms, they treat the model parameters as random variables, where in UCD, or this is very famously called uh, uh, frequentist approach to the problem. There, your model parameters are considered as something fixed, and you construct confidence interval around your uh, uh, parameter, and say with this much probability our true parameter lies in the confidence interval. So yeah, these are two different families of algorithm, and yeah, it's nice to have a look at this code. And yeah, so for this example in particular, Thompson sampling has performed much better. But I think you can generate some problem instance where UCB will probably perform better. Yeah, so that's it. If you have any suggestion and any other things to share, you can mail me in my mail ID. I hope you have it, right? If you don't, just tell me, I'll type it. Okay, so we can stop today's tutorial here. Thank you.
Thank you, sir.